Now see, this is the device that is known as Venturimeter, which is used to measure the rate of flow of liquid. Now see here, there are two coaxial tubes or the pipes like A and C, which are the wider one, and there is one the narrow pipe B, which is connecting these two A and C. Now if we want to measure pressure difference at these 2 points, there is a manometer is connected here, and this manometer, one end of the manometer is to this on the pipe A, and which is wider one, and another end of this manometer is connected to the point B, which is narrow one. Now when the liquid is flowing through this, see here, according to the equation of continuity, you know it, A1 V1 is equal to A2 V2 is equal to V. Capital V is here, I have taken here the rate of flow of liquid. So now see here, A1 V1 is equal to A2 V2. So where area of cross section is smaller one, so at this point is area of cross section, that is A1, and at this point area of cross section is A2. So A1 is greater than A2, so obviously velocity at this point is less than this one. It means kinetic energy at this point is lesser than the kinetic energy at this point. Because of that, pressure energy is here the larger at this point, and at this point pressure energy is less. So we can get at this point, suppose pressure is P1 and at this point pressure is P2. Now low density liquid is filled up here in this manometer. Suppose the density of the liquid we can take here, that is rho L. So density of liquid in manometer. Now both the tubes axis of these tubes at the same level, so there is no change in gravitational potential energy. So we can write total energy at the point A is equal to total energy at the point B. So we can write here P1 upon rho, this is the rho is the density of this liquid which is flowing, plus half V1 square is equal to P2 upon rho plus half V2 square. This is here. Now we can write in this case P1, this we can take to this side everything that shift and velocity to that side. We can get P1 upon rho minus P2 upon rho is equal to half V2 square minus V1 square. Now we can write P1 minus P2 is equal to half rho into, in place of V2 we can write here V2 is equal to V upon A1 and V upon A2, and V1 is equal to capital V upon, this is V1 is equal to this, by using the previous equations or the equation of continuity. Here the V is the capital V is the rate of flow of liquid. So we can put the values of V1 and V2 over here. So we will be getting here V upon A2 square minus V upon A1 square. Now we can solve it further. P1 minus P2 is equal to half rho, and here V, this is V square. So here we can take common V square, and we can write here A1 square minus A2 square divided by A1 square A2 square. This is the equation here now. Now we can go further for this is a P1 minus P2, that is the pressure difference between these 2 points. Due to higher pressure, liquid is here going down, and due to less pressure, liquid is rising here by the height h. So we can also write in place of this P1 minus P2, we can write here the pressure difference formula, and that we can take H rho Lg, that is the density of the liquid in manometer, is equal to half rho V square A1 square minus A2 square upon A1 square and A2 square. Now, we can simplify it. We can get V square is equal to twice of H rho L G A1 square A2 square upon here rho A1 square minus A2 square. And now we can also write V is equal to under root of twice of H rho L G divided by rho into A1 square minus A2 square into A1 A2. So, here this rho is the density of the liquid flowing through this tube and rho L is the density of the liquid in the manometer. H is the height differential in these two labels, and now A1 and A2 are the area of cross section of the wider tube A and narrow tube B. So, by putting all these values you can calculate the amount of liquid, that means the volume of the liquid flowing per second through this tube.